Welcome to the Crazy Hat Chemist. So here's another video on solubility, but before I get started, don't forget about, I got really cool t-shirts here. If you donate to my website, my web address is on the back there. Super cool t-shirts, as well as awesome stickers. So don't forget about getting one of those for your hydro or your computer. Super cool. All right, so let's get started with this here. Bam! So today we are talking about the solubility example number 4. We're going to determine the solubility of ferrous hydroxide. Ferrous is iron 2. Okay, the KSP is equal to 1.6 times 10 to the negative 14 at 25 degrees Celsius. Okay, remember all K values are temperature dependent, so therefore we do need to include that temperature. Okay, we're going to write the equation and then we're going to do that ice table here because this is an equilibrium problem here. So ferrous is a 2+, hydroxide is a polyatomic ion with a 1- charge. You should know that one very well. So here we go. We got ferrous hydroxide, which is Fe in parentheses OH with a 2 subscript. That's a solid. That disassociates to give me a ferrous 2+ ion and 2 hydroxide ions. Both of the ions on the product side are aqueous, okay, and those equilibrium errors lies predominantly on the reactant side, as you can see with that KSP times 10 to the negative 14 that this is a reactant favored reaction. Okay, now I need to do this ice table because all equilibrium problems are just like an ice table. So initial, change, equilibrium. Now, do I need to worry about the ferrous hydroxide because it's a solid? Absolutely not. Because it is a solid, is not going to be included into the KSP expression of any kind. So we're going to get rid of that part. Okay, but the iron and the hydroxide initially, what do you have initially all the time? 0 and 0. Just like any equilibrium reaction. Now, the change, now that part is going to be different. Okay, now for the solid itself, we're going to ignore that. But the change, we're going to shift this towards the product side. So we're going to have plus and a plus. That's a plus sign and a plus sign for both the products. Okay, now we're going to use the stoichiometric coefficient. So what's the stoichiometric coefficient for the iron? That's a 1. So therefore, there's going to be plus 1x. What's the stoichiometric coefficient for the hydroxide? That's a 2. So this is going to be a plus 2x, just like what I got right there. Now what we're going to do is we're going to add up the initial and the change, and we're going to get the equilibrium values here. Again, for the iron hydroxide, the ferrous hydroxide, I really don't care about that because, well, it's a solid. So we don't need to worry about that. And then it's 0 plus the plus x, and that's an x, and then we got a 2x. So hopefully that works out. Simple for you. Now what we're going to do is we're going to write the KSP expression for this. So writing the KSP expression for this, that is products over reactants with the stoichiometric coefficients as exponents. Solids are not included. So I got KSP is equal to ferrous, that's at Fe2+ aqueous, in brackets to the exponent of a 1, and then times hydroxide, that's OH minus 1 aqueous squared. Okay, and where is that squared term coming from? That's coming from the balanced equation, just so that you understand. Now, I do actually have the KSP value. I'm going to substitute in for that. I am looking at the equilibrium portion of my ice table. And what am I going to substitute in for the Fe2+? That's the ferrous ion. Well, that's going to be an X. What am I going to substitute in for the hydroxide ion? That's the OH1- ion. That's going to be a 2x. So now I'm going to substitute all these things in here. Hopefully you are understanding and aware of where all these numbers are coming from, either the exponent terms or the x terms. So now I've substituted into my KSP expression. I have 1.6 times 10 to the negative 14. That's equal to quantity x times 2x quantity squared. Okay, just like what I did before, okay, I'm going to simplify the 2x quantity squared, and I'm going to get 4x squared. So I have 1.6 times 10 to the negative 14 is equal to x times 4x squared. Now I'm going to take 4x squared times x, that's going to equal to 4x cubed. The 4x cubed is equal to the KSP value, which is 1.6 times 10 to the negative 14. Now what you need to do is you need to simplify this and solve for x. So you're going to divide both sides by 4, then take the cube root. Okay, so that's what I've done right here. It's 1.6 times 10 to the negative 14, divide by 4, take the cube root. See, there's a cube right there. It's not the square root, it's the cube root. Okay, I'm going to plug this all into my calculator. Hopefully you are aware of how to do that, and this is the value you're going to get. It's 1.6 times 10 to the negative 5. What is this? Well, this is the solubility because this is what X equals. X is always equal to the solubility. So, X is also equal to the ferrous ion concentration, which of course if you're asked for the ferrous ion concentration, that's equal to the solubility since they are both equal to X, and that is 1.6 times 10 to the negative 5 molar. What is the hydroxide ion concentration? Now that is not equal to the solubility, so you're going to take X and multiply it by 2, just like the equilibrium ice table tells you to do, and you're going to get 3.2 times 10 to the negative 5 molar. Fantastic. Now we're not done, so hold on. Okay, what is the solubility in grams per liter? So we're going to look now for X, and we're going to find out the molar mass for ferrous hydroxide and use that and cancel out our units of moles, and we're going to get grams per liter. So I've taken the 1.6 times 10 to the negative 5 moles per liter, that is the molarity, that's what the solubility is, that's what X is, and I multiplied this by the molar mass of ferrous hydroxide. And then you should see that the moles cancel out, and you're now left with grams per liter. And this numeric value is 1.4 times 10 to the negative 3 grams of ferrous hydroxide per liter. And that is the solubility in grams per liter. All right. I am the Crazy Hat Chemist, and of course you can't get away without having a crazy hat. Give me a thumbs up if you like that video. Subscribe to my YouTube channel. Pass on my YouTube channel to anybody that needs help in chemistry. I'm here for your help. I'll see you next time. Bye for now.